In this video, we're going to go over the Friedel-Crafts alkylation reaction and also the acylation reaction. So let's start with benzene. In the Friedel-Crafts alkylation reaction, we are going to add an alkyl halide. Let's use Tert-Butyl chloride, and we need a Lewis acid catalyst. We're going to use aluminum chloride for this particular reaction. Now the product of this reaction, all we're going to do is replace the hydrogen with an alkyl group. The chlorine group is a leaving group, so we're just going to take this out and replace the hydrogen with the Tert-Butyl group. So that's the main idea behind the Friedel-Crafts alkylation reaction. You're replacing the hydrogen with an alkyl group. But now let's propose a mechanism for this process. The Lewis acid catalyst assists with the formation of a carbocation. Aluminum chloride has 3 bonds, so it has an empty p orbital, which makes it easy for chlorine to donate a pair of electrons to it. When that happens, aluminum is going to have 4 bonds, at which point it's going to have a negative formal charge. Chlorine is going to have 2 bonds, so it's going to have a positive formal charge. At this point, the carbon-chlorine bond is going to break. Because chlorine is more electronegative than carbon, when that bond breaks, chlorine is going to pull those 2 electrons toward itself, giving us a tertiary carbocation. The side product is AlCl4-, which can convert back into AlCl3 and Cl-. So now we can react the benzene ring with the carbocation. The carbocation, which is electron deficient, is the electrophile. Benzene, which has more electron density relative to the carbocation, is the nucleophile. The electrons always flow from the nucleophile towards the electrophile. So when the benzene ring binds with the carbocation, it's going to lose the double bond initially. Now the carbon that binds to the carbocation, that carbon will be neutral. The other carbon, which lost the bond but didn't regenerate a new one, it's going to have a positive charge. That's where the carbocation is located now. So now what we need to do is we need to use a base to remove this hydrogen. This hydrogen is relatively acidic when it's adjacent to a carbocation. So we can use the chloride ion to act as a weak base to remove this hydrogen. The carbon-hydrogen bond is going to break. Those 2 electrons are going to be used to regenerate the pi bond. And so now we have our product. Tert-Butyl benzene. So this type of reaction is known as an electrophilic aromatic substitution reaction. We've replaced the hydrogen with an electrophile. So that's why it's called an electrophilic substitution reaction. And this reaction is associated with aromatic rings. So that's the word electrophilic aromatic substitution reaction. Let's try another example. Go ahead and predict the major product of this reaction and also propose a mechanism. So we're going to react benzene with methyl chloride using the aluminum chloride catalyst. Feel free to pause the video and work on this example. So we know what the major product is going to be. All we need to do is get rid of the chlorine atom and attach the CH3 group to the benzene ring. Now keep in mind there are other products, but this is going to be the major product if we use a 1-to-1 ratio between benzene and methyl chloride. But now how can we propose a mechanism for this particular reaction? So the first thing that's going to happen the methyl chloride will react with the Lewis catalyst. So this step is similar to the last step. And so we're going to get this intermediate. The aluminum atom has a negative formal charge, and chlorine will have a positive formal charge. Now, in the last example, we broke the carbon-chlorine bond, and we generated a carbocation. We can't do that in this example because a methyl carbocation is very unstable. A tertiary carbocation is a lot more stable than a methyl carbocation. And we know that tertiary carbocations can easily form, but methyl carbocations, they're not going to form. So for the mechanism, we can't do that. Instead, at this point, we can use the benzene ring. The benzene ring is going to attack the methyl carbon, breaking the carbon-chlorine bond, avoiding the formation of an unstable carbocation intermediate. So now the plus charge is on this carbon. Here we have AlCl4-, which can dissociate back into AlCl3 and Cl-. So now let's use a chloride ion to get rid of the hydrogen, forming the double bond. So now we have our product. This product is called toluene. Now, there are some limitations with the Friedel-Crafts alkylation reaction. For example, when we mix benzene with methyl chloride, toluene is not the only product. Even though it might be the major product in a 1-to-1 ratio, it's not going to be the only product. Toluene is more reactive than benzene, and the reason why it's more reactive is because the methyl group is an electron donating group. It's a weak activator, so it makes the ring more reactive than the benzene ring. Because it's more reactive, multiple alkylations will occur. This will react with another methyl chloride, producing a Xylene intermediate. Xylene is when you have two methyl groups on a benzene ring. Now this group, the methyl group, is an ortho para director. It will direct a second methyl to go in the ortho position or in the para position. Ortho is 1,2, para is 1,4. So we can get this product, plus we can get the other product. Now having two methyl groups makes the ring even more reactive than having one methyl group. So we can get trimethyl benzene rings. And so polyalkylation or polyalkylated products can form in the Friedel-Crafts alkylation. So that's one limitation of this reaction. Another limitation is that the Friedel-Crafts alkylation reaction does not work if there's any strongly deactivating groups like a nitro group or benzene sulfonic acid. Now let's understand why. So let's put a nitro group on to benzene. The nitro group is an NO2 group, but I'm going to draw it out. One of the oxygens have a negative formal charge and the nitrogen has a positive formal charge. Now let's draw the resonance structure of nitrobenzene. So because it's an electron withdrawn group, the nitro group can pull electron density away from the ring, leaving a positive charge on the ring. And you can see this by means of drawing the resonance structure. If we take a double bond and move it towards the nitrogen atom, this pi bond is going to break, giving us this particular resonance form. there's going to be a double bond between the carbon and the nitrogen, and these two oxygens will have a negative charge. The nitrogen still has a positive charge. It still has 4 bonds. But the benzene ring now has a positive charge. So in that sense, the NO2 group is an electron withdrawn group. It pulls away electron density from the benzene ring, putting a positive charge on it, making the ring less nucleophilic, more electrophilic. So this ring is less reactive towards electrophilic aromatic substitution reactions. However, it's more reactive towards nucleophilic aromatic substitution reactions. Now, the Friedel-Crafts alkylation reaction is an EAS reaction, or an electrophilic aromatic substitution reaction. And the reason why it fails is because we want this ring to be a nucleophile, not an electrophile. If the ring has a positive charge, it's not going to want to react with a carbocation that has a positive charge. Like charges, they repel each other. These two are not going to interact. So they're just going to feel a force that's going to cause them to move apart. So that's why the Friedel-Crafts alkylation reaction fails if you use any strongly deactivating groups. It's going to make the ring positively charged, which is not going to interact with a positively charged carbocation. So no reaction here. Now there's another limitation, but before we discuss it, I want you to predict the major product of this reaction. So let's react benzene with propyl chloride using the aluminum chloride catalyst. What do you think the major product will be? Do you think it's going to be propyl benzene? What would you say? It turns out that propyl benzene is not the major product. The major product is isopropyl benzene. So another limitation of the Friedel-Crafts alkylation reaction is that you can potentially have carbocation rearrangements if the structure allows for it. Notice that the chlorine atom is on a primary carbon. If a primary carbocation were to be produced, which is difficult to do, they're not stable, it can rearrange and form a secondary carbocation, and the benzene ring attacks the secondary carbon. So in this reaction, a carbocation rearrangement has taken place. So now let's propose a mechanism to go from benzene to isopropyl benzene. And we'll talk later how to produce this particular molecule. So let's start with propyl chloride, and let's react it with the aluminum chloride catalyst. So these two are just going to combine with each other. Now we don't want to break the bond and form a primary carbocation because primary carbocations are not stable. Instead, what we want to do is perform a hydride shift so we can go directly to a secondary carbocation and avoid the formation of an unstable primary carbocation. So the carbon-hydrogen bond is going to break, and the hydride ion is going to attack the primary carbon, expelling this entire group away. So now the plus charge is on the secondary carbon. At this point, the benzene ring is going to act as a nucleophile, attacking the secondary carbocation. So now we have a plus charge on this carbon. And in the last step, we're going to use chloride to get rid of the hydrogen and regenerate the aromatic ring. So this is the product of the reaction. On the test, if you were to see benzene with an alkene that looks like this, 2-methylpropene with HF. What would you do? Now this is just another variant of the Friedel-Crafts alkylation reaction. It's just you're finding other ways of generating carbocations instead of using an alkyl halide. So let's talk about what's going to happen here. So first, the alkene reacts with HF. The double bond attacks the hydrogen, expels the fluoride ion. So as the hydrogen is added to the less substituted carbon, that is the primary one, we're going to have a tertiary carbocation. And the fluoride at this point is somewhere in the solution. Now the benzene ring is going to react with the tertiary carbocation, as it always reacts with it. And then in the next step, we're going to use fluoride instead of chloride as a weak base to remove the hydrogen, regenerating the aromatic ring. And so we're going to get Tert-Butyl benzene again. Now, starting from benzene, how can we make propylbenzene? So we know we can't make it using the Friedel-Crafts alkylation reaction, but how can we produce this product? We can make it using the Friedel-Crafts acylation reaction. So first, we need to add an acid chloride using the aluminum chloride Lewis acid catalyst. What's going to happen is this is going to turn into a ketone. The chlorine is going to leave. And once we have this ketone, we can reduce it into an alkane using the Clemmensen reduction, which is a mixture of zinc, mercury, and HCl. Or we can use the wolff-kishner reduction, which is hydrazine and an alkaline solution of potassium hydroxide or sodium hydroxide. Hydrazine can be written this way as well. You might see it as H2N, NH2, or N2H4. But now let's talk about the mechanism of the Friedel-Crafts acylation reaction. So first, the acid chloride reacts with the Lewis acid catalyst. So those two combine. And then the chlorine atom detaches from the carbonyl group. And so we're going to get an acylium ion. So at this point, the carbon has a positive formal charge. However, oxygen can use one of its lone pairs to stabilize that positive charge. So that positive charge is shared between the oxygen atom and the carbon atom. So the acylium ion is stabilized by resonance. But we're going to use this form to react with the benzene ring. So let's draw benzene once more. And here's the acylium ion. And benzene is going to act as a nucleophile, reacting with this ion. So now we have a ketone, but we still have a plus charge that we need to get rid of. So we're going to use the chloride ion as a weak base to remove the hydrogen and regenerate the benzene ring. And so this is the product of the Friedel-Crafts acylation reaction. At this point, if you want to make propylbenzene, you can now reduce it with the zinc, mercury, and HCl, or we could use hydrazine and hydroxide by means of the wolff-kishner reduction. And so now you know how to make propylbenzene. So you can't use the Friedel-Crafts alkylation reaction to make that compound. You have to use the Friedel-Crafts acylation reaction to do it.